So the topic of this video is the elastic pendulum, and obviously to explain that I have to start with a dog. I'm not going to name this dog Elon Musk, even though I heard that if you use the word Elon Musk in a video you get a lot more clicks, but I'm not going to stoop that low, so I'm not going to name this dog Elon Musk, but I'm going to show you what's going to happen if I change the gravity in this software. See, the strength of gravity is increasing and now I'm decreasing it. And the simulation software that I'm using here is AlgoDo. You can see the link down there or in the description. Now I want to use this software to simulate this spring pendulum. And first of all, we have a spring here with a spring constant of 30 newtons per meter. And the mass hanging from the bottom of the spring is 1 kilogram. Now, in this software, you can turn friction and air resistance on and off. And as I already said, you can change the strength of gravity. Right now, it's set to 5 meters per second squared. That is lower than Earth gravity. And now I'm going to bring in my hand and pull that pendulum down to set it in motion. And as you can see, the mass at the bottom of the spring also has a tracer attached to it that actually paints a trace of the trajectory. So let's try changing gravity up to 10 meters per second squared. That's close to the value we have here on Earth. And as you see, it's still doing that vertical oscillation because I let it go the same way as before. But now you see something different is happening. And that's the weird thing that has to do with autoparametric resonance. But there it goes back to a vertical oscillation. It's almost as if this stretchy pendulum has a mind of its own. Let's see if it stays vertical, but no, you see it doesn't stay vertical, it goes back into this sideways pendulum-like oscillation. And if we wait long enough, it's going to return to that vertical bobbing motion, and there it is. But now let's crank up gravity even more. This is an extremely high gravitational acceleration of 30 meters per second squared. And when I let the pendulum go the same way that I let it go before in this vertical direction, it stays vertical. You can wait as long as you want, but you're not going to see it fall into that sideways pendulum motion anymore. So as for the case of 5 meters per second squared, that weaker gravitational acceleration that we started with, this extremely strong gravitational acceleration has again stabilized the vertical motion for some reason. And lastly, let me go back to a slightly lower acceleration of gravity of 15 meters per second squared, and you see that it's now doing this flip from vertical oscillation to pendulum-like oscillation and back again. Now, actually, what you're doing when the acceleration of gravity is changed is you simply change the ratio between the natural frequency of oscillation of the pendulum, the left-right motion, and the natural frequency of the spring at which it wants to oscillate. So as we changed the ratio between these two natural frequencies, we were going from a regime where a vertical oscillation is stable to one where the vertical oscillation was not stable, and then back to a regime where the vertical oscillation was stable again. The nice thing about doing simulations of a system like this is that you can explore this parameter space of different strengths of gravity, for example, much more quickly and automatically. For that, I use one of my other favorite toys, Mathematica, to solve the equations of motion for this system given different strengths of gravity. And in this context, one important thing that we have to keep in mind is that if there's no air resistance or friction of any other kind, then this whole thing is energy conserving. The force of gravity and the restoring force of the spring are both conservative forces, as one calls them. And that means although these two types of motion can exchange energy with each other, the total amount of energy in the system stays the same at all times. And when you have a system where the energy is conserved, it's really useful to think about the kinetic and potential energy of the object that's moving around, and that's the bob or mass at the end of this spring. That's shown here in the colored contours that range from yellow for high potential energy to blue for low potential energy. And as I've drawn it here, the mass at the end of the spring right now is at its equilibrium position where the downward pull of gravity is just balanced by the upward pull of the spring. So it could stay at rest in that position. But of course, we're going to pull it down and then let go to launch it into an oscillatory motion. Don't worry too much about the numbers that are used here on the horizontal and vertical axes for the x and y coordinate. Y is the vertical coordinate here. What matters is where the object is in relation to the potential energy landscape, and that landscape is created both by gravity and the elastic potential energy of the spring. So just for reference, I put a white dot at the top of the spring to remind ourselves where that spring is attached. But when I run the simulation, I'm going to just erase that spring so that the motion of the bottom of the spring, the mass that's actually creating the trajectory, becomes easier to see. The valley of potential energy that this mass is in has a shape that depends on the ratio between those two natural frequencies of the spring and the pendulum. And basically in the simulation, I call that ratio alpha. The way it's defined here, small alpha corresponds to large gravity and large alpha corresponds to small gravity. So as I increase alpha from the current value of 1.5 that it has here, you'll see the equilibrium position of the potential energy valley shift upward because gravity gets weaker in comparison to the spring force as I do that. And to save time, what I'll do is I'm not going to follow the motion of the mass as it moves around, but instead I'm just going to draw the entire trajectory of the mass as a red line, and the animation is just going to consist of me ramping up alpha and showing you the pictures for the entire trajectory that I got as a result. There it goes. So right now you see the red line is vertical. That means the mass was able to stay in a vertical oscillation, but as alpha reaches a critical value, suddenly the trajectory fans out to the sides. That's that switch to pendulum-like motion. At the end, when alpha got really large, the trajectory shown by the red line collapsed back into a nice vertical line, which means that a motion launched in the vertical direction stayed vertical again. By the way, the reason why in that intermediate regime the trajectory fanned out to the left and right was that I actually intentionally launched the mass in a slightly wrong direction, slightly away from the vertical direction, but imperceptibly on the scale of this drawing. But now I want to exploit that idea a little further to illustrate what's really going on here. And so what I'm doing in the next animation is I recorded the trajectories of the mass for two slightly different ways of launching them at the beginning. On the scale of these x and y coordinates, the deviation from a perfect vertical is of the order of 0.1%. So it's really tiny. And that's why initially for small alpha, where I'm starting here, the trajectory is again able to stay vertical. But for alpha around 3, not only do you see the trajectory making those excursions to the left and right, you also see that the red and orange lines, which indicate the two different trajectories that differed only by slight amounts in their initial conditions, trace out different paths. The motion really seems to have become unstable in a fundamental way. And also shown here are the cyan dots here. They mark the end points of the trajectory for the red line and the orange line as I followed them for the exact same amount of time from almost the exact same initial conditions. And as you can see, the two cyan dots for the two different trajectories, although they started very close to each other, are now quite far away from each other, measured relative to the size in this plot of the region that is allowed to be filled in by these red and orange trajectories in the first place. That region itself is bounded by the condition that the total energy has a certain value, which prevents the trajectory from ever leaving this lentil or lens-shaped region. But within that region, the endpoints of these two neighboring trajectories are now quite far away. They have diverged, play a few steps further than we are here, and again you see the endpoints have different locations. And what this illustrates is a phenomenon that's called sensitive dependence on initial conditions, which is one of the hallmarks of dynamical deterministic chaos. And that's really what we're seeing in this stretchy spring pendulum. The condition for autoparametric resonance is a convenient way to estimate at which values of the gravitational strength this transition to chaos occurs.